Okay, so in class last time we talked about how pitch affected how you perceive sound. That pitch was your perception of the frequency of the sound wave. We mentioned how intensity also affected how you perceive sound, and that's related to the loudness of a sound. Now, relating intensity to loudness is not very straightforward because intensity is a objective thing. It's easily measured and quantified. And in the last chapter, we looked at calculating the intensity of a wave if you know the power of the source and your distance from the source. And we used watts per square meter as the unit for intensity. Well, the way that you perceive that intensity is loudness, and that is something that's actually very subjective. And the relationship between intensity and loudness, obviously there is a relationship because the more intense a sound is, the louder it sounds, but that relationship isn't necessarily easy to figure out. So in order to understand this, we first need to understand that there are two units that we use, two scales that we use. They're related, but they're two different scales. We have the intensity, which is the objective measure of how much energy a sound wave carries. That's measured in watts per square meter. And then we have the loudness, which is a measure of how loud that particular wave seems. And we use units of decibels to measure loudness. Now, they're related to each other, and in order to understand this relationship, we first need to define kind of a baseline, a starting point. And for that, we've come up with this idea of the threshold of hearing. The threshold of hearing is an intensity of 1 times 10 to the negative 12 watts per square meter. That's on average the faintest sound that a person can hear at a frequency of 1,000 hertz. Now, we're picking 1,000 hertz kind of arbitrarily just because that's kind of in the meat of that audible range that we talked about. The threshold of hearing would be different if we were to look at a different frequency. Remember how as we swept through the audible range, sounds that were close to the lower end of 20 hertz and the upper end of 20,000 hertz seemed quieter, even though their intensity was the same. So the threshold of hearing, if we were to look at it for, let's say, 15,000 hertz, would be something much higher than this. Or for 20 hertz would be something higher than this. So we just pick 1,000 as kind of a baseline average frequency. So that's the quietest sound that a person can hear. On the other end, there is kind of a maximum intensity that a person can hear. We call this the threshold of pain. And for the average person, that's about 1 watt per square meter. We call it the threshold of pain because if the intensity exceeds this I max, we could say, then you're no longer able to perceive sound, you actually perceive pain. It physically hurts. And on the decibel scale, we define this as 0. And this turns out, as you'll see in a homework problem that you have, this turns out to be around 120 decibels. Okay? So let's look at this relationship between intensity and loudness. As I mentioned, the relationship isn't necessarily straightforward because if you want to double the loudness of a sound, let's say we take something that's at the threshold of hearing, a sound that you can just barely hear, 1 times 10 to the negative 12 watts per square meter, and you double this intensity, that would give you 2 times 10 to the negative 12 watts per square meter. That would be a sound that is twice as intense, but it would not be close to being twice as loud. If you wanted to actually get a sound that was twice as loud, you would have to way more than double the intensity. All right? That's because if we look at the range of intensities that your ear can perceive as sound, from 1 times 10 to the negative 12, that's an extremely small number, extremely small, almost 0, all the way up to 1 watt per square meter. Now, 1 may not seem like a very big number, but compared to this, it's huge. So this is a very, very, very broad range of intensities that your ear can hear. So in order to make sense of this extremely broad range of intensities, we have to build the loudness scale, the perception of these intensities, around a logarithmic scale. Now, a logarithmic scale is based on powers of 10. Okay, the best way for me to kind of help make this make sense is to use an example. So let's say we have loudness measured here in decibels and intensity measured here in watts per square meter. I'm not going to use actual numbers for the intensity. I'm just going to use, let's say that the original intensity is for the initial intensity, okay? And we're going to look at how much that intensity increases as we increase the perceived loudness. We're going to put some numbers to this in a second. I've got a couple of examples where we'll actually calculate the actual intensity for a specific decibel level, but that's not what I want us to get right here. So let's say that we start with a sound that has a loudness of 20 decibels. All right, so the perceived loudness is 20 dB. That's going to be associated with a specific intensity. Okay, and like I said in an example here in a minute, we're going to calculate how you can figure out exactly what this intensity is. All right, let's just look at how the loudness changes as the intensity changes. Okay, if we want to increase the loudness to 30 decibels, that's an increase of 10 dB. Okay, that's not a very large increase in perceived volume. All right, since this is on a logarithmic scale, though, the increase in intensity required to produce this increase in perceived loudness is 10 times the original intensity. So an increase of 10 dB corresponds to a factor of 10 increase in the intensity. If we wanted to increase the decibel level to 40 dB, right? That's an increase of 20 dB from our original sound. That corresponds to a 100 times increase in the original intensity, right? The 40 decibel sound is twice as loud, okay? 40 dB is twice as great as 20 dB, so that's a perceived volume that's twice as loud as our original sound, but it is 100 times more intense than our original sound, okay? A much greater increase in the intensity. If we wanted to increase the decibel level to 50 dB, right, an increase of 30 decibels, that would correspond to an increase of 1,000 times, a factor of 1,000 increase from our original intensity, right? Vastly greater increase in intensity for a modest increase in volume. If we wanted to increase it to 60 dB, can you guess what the factor, by what factor the intensity would have had to have increased? Here it's increasing by a factor of 10 for an increase of 10 dB. An increase of 20 dB results in an intensity increase of 100. 30 results in an increase of 1,000. A 40 dB increase will result in our intensity increasing by a factor of 10,000. Right? So if we wanted to go up to 70 dB, that would correspond to an intensity that is 100,000 times more intense than our original sound. Now this is nowhere near 100,000 times louder, but this sound is 100,000 times more intense. Okay, so we have a very, very broad range of intensities that you can hear that correspond to not nearly as broad a range of volumes that your ear perceives. Okay, so now let's do some examples using the equation that describes this. So yeah, that's just explaining what I just was telling you. And there's the equation that we're about to use in some of these examples. All right, so let's do some examples using the decibel scale, that equation relating the decibel scale to the intensity. A stereo is turned up from 45 decibels to 50 decibels. What is the change in intensity of these two settings? So we've got the two decibel scales, the decibel readings, and we want to find the intensity that's associated with each of these settings. So basically we're going to do two problems where we find the intensity for 45 decibels and the intensity for 50 decibels and then compare the two answers that we get. So let's do this for 45 decibels first. So we're going to look at 45 dB sound. That's the decibel scale. We use the Greek letter beta to represent the decibel scale. We want to know the intensity associated with that decibel level, with that loudness. We know that the intensity of the threshold of hearing is 1 times 10 to the negative 12 watts per square meter. So we'll use this equation. And we want to solve it for I. We know the decibel level is 45, 10 log I. And we know what I0 is, but I'm going to plug that in later. So we just need to do the algebra solving this for I. So we want to undo everything that's being done to I. So first let's get rid of the 10. That means we divide both sides by 10. So we get 4.5 is equal to log I over I0. The next thing we need to do is get rid of the log. Now this is going to force you to remember back to your college algebra class. The log, remember, is the inverse of raising 10 to the power of some number. So in order to do the inverse of the log, you have to raise 10 to the power of that log. So to undo the log here, we take 10 and raise it to the power of log I over I0. What we do to one side, we have to do to the other. So we have to say 10 raised to the 4.5 power. So let me rewrite this in a way that maybe looks a little more familiar. On this side, we have 10 to the 4.5 power. On this side, we have 10 raised to the log I over I0. Okay? So here we can calculate what 10 to the 4.5 power is. That is 3.16 times 10 to the 4th. And here, the 10 and the log cancel each other out, and we're left with I over I0. And now we have an equation that's easy to solve. We multiply both sides by I0. So on this side we have 1 times 10 to the negative 12, that's our threshold of hearing, times 3.16 times 10 to the 4th is equal to the intensity that we want. Work this out, and we get the intensity associated with the 45 decibel sound is 3.16 times 10 to the negative 8 watts per square meter. All right. Now we want to do the same thing for the 50 decibel sound. So we know the decibel level is 50. We want to find the intensity associated with that. The threshold of hearing is still 1 times 10 to the negative 12 watts per square meter. So we basically just do the exact same thing, starting with the same equation. Go ahead and plug the 50 in. So first we'll divide both sides by 10, so we have 5 is equal to log of I over I0. Next, to undo the log, we raise 10 to the power of what's on both sides. So over here we have 10 to the 5th, and here the 10 and the log cancel out. So we're left with I over I0. So now we multiply both sides by I0. So we have 10 to the 5th times 1 times 10 to the negative 12 watts per square meter. Gives us an intensity of 1 times 10 to the negative 7th watts per square meter. So this is the intensity of the 45 decibel sound. This is the intensity of the 50 decibel sound. Now, notice these two numbers. It may not be immediately clear, but the thing I want you to see here is if you were to turn your volume knob up from 45 to 50 dB, that would be a very, very small change in volume. You might not even be able to perceive that the 50 decibel sound is louder than the 45 decibel sound. It's not a very big change in volume. But this is actually a very large change in intensity. Okay? These are very small numbers, but notice that it's changed by a factor of going from -8 to -7, okay? That is almost a factor of 10. Not quite a factor of 10, but almost a factor of 10 change there. So it's a very large change in intensity for a very small change in loudness, perceived loudness. All right, here's another example. In a car, a rider sits about 0.8 meters from a speaker that is outputting 15 watts of sound power. What is the loudness perceived by the listener? Okay, so here, we eventually want to use this equation and calculate the decibel level, because we are asked to calculate the perceived loudness. That's measured in decibels. In order to calculate this, we need to know the intensity of the sound, which isn't directly given to us, but we are given information that we can use to find the intensity of the sound. We're given the distance from the source to the listener, and we're given the power output of the source. So we can use this equation from the previous chapter. Sorry. Intensity is equal to power over 4 pi r squared, power over the area of the sphere that the sound is being distributed over. The power of the source is 15 watts over 4 pi. The radius then is going to be the distance between the sound source and the listener. That is 0.8 meters. That gets squared. So the intensity of this sound at 0.8 meters from the sound source comes out to be 1.86 watts per square meter. Now that's not the loudness, that's the intensity of the sound. We now want to use this equation to calculate what the perceived loudness associated with this intensity is. So we plug this number in for I, 1.86 watts per square meter, over the intensity of the threshold of hearing. Now notice that these units cancel each other out. The decibel really isn't a unit, it's a ratio. So it's the placeholder for a unit. It's the ratio of the intensity of the sound that you're listening to the intensity of the quietest possible sound that you could hear. Right? So it's kind of a made-up arbitrary unit. So now we want to work through the math here. So first I'm going to divide these two numbers. That gives me 1.86 times 10 to the 12th. Take the log of that. Make sure you're careful in the way you plug that into your calculator. When you take the log of this number, you should get 12.3. This is then 10 times 12.3 multiplied by the 10, and you get 123 decibels, which incidentally is above the threshold of pain. Right? So 0.8 meters is about how far away from a speaker you would be sitting in a car, and 15 watts is a pretty standard power for a factory car speaker. So if you crank that thing up all the way so that it is putting out the full 15 watts of power that it's capable of putting out, you can produce a sound that is definitely above the threshold of pain and actually cause hearing damage. Now this is of course assuming that all 15 watts of power that go into the speaker is being transferred into sound power, meaning that the speaker is 100% efficient, which isn't true. There's no such thing as anything that's 100% efficient. Some power is lost in heating up the speaker. Some of it's lost in friction as the speaker moves back and forth. But you can still do some serious hearing damage even with a relatively weak speaker.